Wendy McDodd. I'm a senior utilities engineer here at the Commission in the Safety and Enforcement Division. I've been with the Commission almost 18 years now. And I've been active in IEEE in our local Power and Energy Society San Francisco chapter for, I guess, about 10 years now. And before I do a further introduction and pass it on, I just want to say this is a volunteer organization, but it's also very important for a lot of work that we're doing here at the Commission. If you are interested in volunteering, even if you are not an engineer, you can volunteer and help us out. We really need help. We're scrambling, we're so swamped and we're busy, and we did a lot to try to get this together, but we could use additional volunteers. I'm a past officer, past chair, and I want to introduce Marty Kurtovich, who is my colleague and is taking on the vice chair role this year for our local chapter. We also have Art Maldonado is our chair, who lives in Naples, Florida, but is a polymer chemist, and it's working out really great that I have a relationship with him because he knows cables, and I'm looking into covering conductor cables for some regular work. So anyway, he's our chair. Our secretary is Charles Mee, who works at the Commission. He couldn't be here today, and Sheng-Yan Shao is our treasurer from PG&E. I will turn it over to Marty, and thank you for coming, and yeah, it'll be good.
Yeah, thanks everyone for coming. This is the first meeting of the year. Question? Yeah. So my name's Marty Kurtovich, and I'm the vice chair this year. And we decided to start it off with a bang by inviting Professor Clements from San Jose State University. A number of us from Safety and Enforcement Division went down to his lab in December to check out what work they're doing. And I don't know if any of you remember the movie Twister, which was about a bunch of guys going out chasing tornadoes. That's basically what he does with wildfires. So he has very up-to-date, current information on wildfires based on their field studies they've been doing over particularly the last 2 years. So without further ado, I'll turn it over to you.
Great, thanks
for coming.
Thanks everyone for coming today, and thanks for having me. It's an honor to be here. I kind of coming off of a little cold, so I'll be drinking water through. So I'm going to talk about the use of mobile atmospheric profiling systems or monitoring systems for kind of real-time analysis and monitoring of wildfire events, particularly in California. So I want to highlight some technology that we're using and stuff that we plan to be using in the future. And so I'll give you some background on observation systems. I want to start off with the role of small-scale experiments because that's kind of where we started, setting up sensor networks to study the small-scale dynamics of wildfire spread, because it's actually something that we still need to understand better. And we don't have a good handle on how large wildfires spread. So I'll talk about some field campaigns, including some aircraft observations, and really highlight vertical wind profiling for fire management and utility management for that matter. So just a refresher, when we think about fire behavior, the fire environment triangle, we have to consider fuels, which are super critical in California. What's burning, what's the condition of those fuels, dry, moist. Most of them are very dry in the fall, of course. And well, I'm biased, I'm a meteorologist, but what I think is really critical is the weather, because weather changes rapidly. It's the fastest changing component. And then if you have a fire in topography, that's even more problematic because fires spread more rapidly in topography or on slopes. So most of you probably remember the Carr fire tornado. It's the largest fire tornado ever recorded. A colleague of mine published a paper recently on its dynamics and kind of how it formed. But we really don't understand the dynamics of how wildfires create their own weather and what role this has on fire behavior. It's something that even fire management tends to like, oh shoot, this thing's a little big, it's burning really fast, and now if we get these big columns of big plumes, then it can be very problematic with something called spotting. When you have embers being transported by the wind, and spot fires can start far distances downwind of the main fire front. So if you're engaging with a fire front that's moving and it starts spotting miles downwind, now you have another fire up ahead of basically the fire suppression resources. This is a little technical here, but basically we can identify different coupling between the wildfire and the atmosphere, and we call this the Vector-Froude number, and it's just basically the power of the fire, which would be heat of the fire, below the wind speed. So it's the ratio of the wind speed versus the heat of the fire. And so we can actually determine if a fire is wind-driven, which most of the big fires in California are wind-driven or a combination of wind and plume dominated. Or if there's less wind and there's so much heat, then the fire is actually driving the weather around it. And so this has been something that we've been studying in numerically with computer simulations, in the field with small-scale experiments, and now what I'll show today later is what we're doing with observing the dynamics of wildfires in real time.
Sorry,
So,
can I ask a really quick question?
yeah.
For the car fire, it's an EF3, is that
It's
a class?
enhanced Vegeta scale.
Enhanced Vegeta.
Yeah, so all tornadoes are with the EF scale, so enhanced Vegeta 3, so that means like 160 mile-an-hour winds.
Nice.
I forget the actual thresholds between the different scales. And if I'm going too fast, just slow me down. I'm used to cranking through slides when I lecture. That's my complaint for students. is going too fast. So the goals of my research program at San Jose State are really the fact that few meteorological observations exist near active wildfires, because they tend to be remote. Now, the fires in the last 2 years have not been remote because they've been burning into major cities or into large towns. We have a limited understanding of how plume dynamics affect fire spread. And there's also a data gap for understanding the next generation fire behavior models. And I'll show you an example of that next. So our goal is to collect comprehensive data sets on active wildfires. Yep, yes.
It's okay, you could finish your sentence there. I was just gonna say, how does in the data collection that you do, how does the new GOES satellites,
Goes Argo 16, Go
Yeah,
17.
that enable like a whole different world on weather, how does that impact what you get on the ground?
Well, the scale,
When you say you have a limited
yeah,
data
well,
gap.
that doesn't show us the weather. That only shows us where the fire is.
Okay,
Right, so it gives us a hot spot, a 2 kilometer by 2 kilometer hot spot.
got it.
Not, and what we need is like meter scale to really understand fire behavior. It's great, no, don't get me wrong. There's other satellites. VIIRS is, I think, 375 meter resolution, but it's polar orbiting, so you get a few snapshots, I believe.
No, but then if you have such a high resolution, you might be blocked by the trees.
Well,
The trees might
yeah, no, these fires, you can see the heat through the trees.
oh,
Yeah, trees aren't that dense in terms of remote sensing. You're talking about 1,500 degrees C, and a tree is ambient. So it's a big signal, yeah. So here's an example of a small scale. This is the French coupled fire. This is the most advanced fire coupling system in the world. That and Warfest fire, which is in the US. But this is what we're talking about. Computing the physics of combustion, linking it to a weather model, and having it spread through a fuel bed. You're able to generate these fields. This is highly computational intensive simulation here. But these are different streamlines are like, I think TKE, the smoke is actually a TKE, a turbulence component. But what you're seeing is this kind of idealized fire spread driven by the atmosphere and the response of the atmosphere from the fire. So you see updrafts and downdrafts and some of this wave motion behind it. And so these are things that we can now model. And I have colleagues that are able to do this in real time, but we need the data to validate these kinds of models. And so this is actually a simulation of a previous experiment I did in 2006, but we went back in so that's basically the state of the art, what we call coupled fire atmosphere model system. It's the French model because I like the simulation. But the Warfest fire model system is also run here. So we've done some small scale grass fire experiments at the same site. We did another burn in 2013, and I'm just going to click through all this. We put a bunch of stuff in the field. We take fuel samples, we do air quality, we measure the wind, we have a Doppler LiDAR, and I'll talk about that. And so we can just saturate a field, and then We have a tall tower with all sorts of instruments to give you scale. That's a person, that's my student. And so this is a 150-foot tower, and so we can just collect everything that we want, and it's great. I'll just kind of, and here's what we can do with that. I'll just skip through this. These are some GoPros. Let's get to it. So. And so we can actually, this is actually one of the first times this has ever been done, where we filmed a experimental grass fire as such, looking down from about 60 feet. So our instruments, you can see the packages and the fuel, and our tower's instrumented with all those sensors. And so as the fire burns through, we can measure the heat, we can measure the radiation, well, the sensible heat flux, the radiative heat fluxes, and all the turbulent quantities, and how the wind interacts with the fire front. Yes?
Did you have to have a really detailed wind profile before you started this fire? Like, was this test based on the dynamics of surface and above surface wind patterns?
This is at the University of Houston. It's private. There was actually a burn ban in the state of Texas. We had to actually get the county judge to sign off on this, like an hour. We missed the Veers was overpass, Modus overpass, and we tried to time it. We missed it by an hour because of the politics. Yeah. Anyway, so these are the kind of things we can do. Yes?
Could you, just really briefly, the difference between LIDAR, sonar, and SODAR, which you also had on here?
Yeah. I'll get into describe LIDAR in depth because we're going to talk a lot about it, but SODARs are acoustic wind profilers that make a chirping sound. They sound like a bird.
Okay.
And so you can hear them, and it bounces sound waves off the atmosphere, and depending on the stability of the atmosphere, it bounces back, and because of the frequency shift, the Doppler shift, you can calculate the wind profile.
Okay.
And those are great tools. But LIDAR uses laser light, so it's much quicker, it's much more efficient, but you need particles in the atmosphere, and I'll show examples during the de-energizing event where we took the LIDAR up to Calistoga, and it worked okay until it cleaned out, and then we get the returns. And then radar is using radio frequency that bounces off of particles in the atmosphere as well. Generally radar is used for rain and cloud droplets. So yeah, those are the remote sensing technologies. And then this just kind of shows if we put everything together and we do a composite, we can see pressure fields driven by the fire. The LIDAR scan is this, I'll point on the screen so people can see. And the big black dots are where the fire front is because we have sensors in the soil. And then this shaded color is where the winds are accelerating, so we see lots of strong winds at the fire front. The blue shading here is actually the low pressure that's created by the fire, which then drives the fire front and the winds behind the fire. And so we can compile all this and look at this very fine structures in the flow around the wildfire, well, experimental fire. And so there's the temperature structure, and there's the wind structure from that big tall tower that I showed earlier. And what you see is that there's acceleration, not much because it's a real strong windy day, and these vector arrows mean that it's a northwest wind. Okay, so that's not down, that's a compass bearing printed on the map or on the figure. So what we expected is that the winds would shift in direction strongly, or a little bit more, not as subtle as it is here. And that's because generally when you have like that, remember that first diagram where if it's not wind driven, we get in-draft circulations from all sides. If it's wind driven, we don't get strong in-draft circulations, and so that's what we're seeing. We see a very modest wind modification ahead of the fire front, but when we get acceleration here, this is where we call fire front passage, and this is the low pressure that we were able to measure. And so this has never been done before on planet Earth. And this data has just been, it's going to be out in about a month. It's just accepted for publication in the International Journal of Wildland Fire. So we can learn a lot from small scale field experiments about the dynamics of fire spread and how the atmosphere drives fire spread.
I have a question. I'm really sorry. You just said a lot of words that I'm sort of aware of.
Okay.
So the line in the middle, that's the draft.
This one?
Yeah. Was that like the front of the fire?
Yeah, that's the max temperature of 350 degrees.
Oh, okay.
And so 350 degrees is, that's like a parcel of hot combustion gases. That's like the fire front hitting the tower.
Oh.
Remember the fire went right through the tower?
Yep.
So that's the temperature of it. Now, the flame temperature is actually higher, but we're measuring these gases just outside the fuel, so we're actually measuring the flame contact. And that 350 degrees, 325 to 375 is ignition temperature. That's what's causing the fire spread.
And so when you talked about wind-driven or plume-driven, then you're saying that the low pressure would follow with the plume-driven when
Yeah.
it hits the right point?
But look at, so if you see how this thing's kind of tilted? All the hot gases are tilted like this. And then for those that are watching online, you kind of see this tilt here, the structure. That's kind of, if it was more plume-driven, it would look like a triangle, right? But since the wind is pushing it from right to left, the wind's blowing this way, you're getting kind of weaker heating up here inside the upper part of the plume, and then real strong heating or high temperatures at the surface, of course. And so that's this wind-driven fire. And so even with this wind-driven fire, we're getting this low pressure.
Mm-hmm.
But it's because there's such strong ambient wind, there's the wind superimposed again. Because there's such strong ambient winds. And again, these aren't winds going this direction, it's actually a northwest wind superimposed on here at 3 levels on the tower. And those winds align with this direction, okay? So it's a real complicated, this is a time height figure, so sorry, but does that make sense of what's going on? So the winds are actually tilting the plume over.
Yep.
They're northwesterly winds. You can see that they kind of slack or weaken behind the fire front. They strengthen slightly ahead of the fire front, and they shift in, they're shifting in direction at the surface. But generally what we see, and I'll show you examples of a wildfire, they shift all the way in. I mean, we get a total reversal. So this is kind of the basic understanding of fire spread and how the atmosphere and the local meteorology drives fire spread in a grass fire. And California has lots of grass fires. But we wanted to develop a program for active wildfire monitoring. So we wanted to go to wildfires. And I'm going to kind of discuss the rest of the talk on how we did that here in California. So all the team members are firefighter qualifications sponsored through the National Forest Service. We're available as a national resource through Ross, so we can be requested. We've been requested to Washington State. We didn't deploy because I didn't have anybody, everybody's on vacation. Students like to take some vacation time too. We've been requested all around the state of California, and et cetera. So that's what we wanted to do. And so what we've just published a paper last month called RADFire, the Rapid Deployments to Wildfires Experiment. This is the campfire, by the way. This is the second day. This is a great picture, but unfortunately our generator broke right here. We pulled the cord without the power. And so we sampled about 24 wildfires, well, 25 wildfires, including like 3 or 4 fires last 2 years. Campfire. Where did we go this summer? We went to a bunch of fires, but I can't remember. But this is the core of the fires that we sampled. And we have basically, you know, we can load up, we can get a call, and we can load up within an hour from San Jose State. On the day of the campfire, we were prepared to, that was a big day. I mean, we were getting filmed by, NPR, I can't remember what PBS, sorry. PBS was filming us the day before, and they went up to the Car Fire site, and I said, oh, it's a big red flag warning, it's a huge wind event. There'll be a fire in California tomorrow. And I said, would you go out? And I said, yeah, we'll go out. So we were ready. I mean, we knew there was going to be ignition because it was a big wind event. Did you know that it was going to be the campfire? No. Did you know it was going to be where it was? No. But we knew these conditions were. So when we're loaded and ready, we just have to get my students to San Jose to drive the truck. So we were on the road by 10. I had to pull students out of class, and we got to the campfire at 1 p.m.
So it's just a matter of having a spot. When you said that, you know that it's the perfect.
Well, we knew there was a big dry wind event coming. And if there was an ignition, you have to have an ignition or you don't have a fire, right? So, and I'll show you some examples of that. I'll just keep going through here. So this is our mobile platform. It's a truck. It's got a bunch of stuff on it. The key platform is this LiDAR, which we also operate on the roof, and we can just have it, running. But we mount it in the back of a truck. And what it does is it shoots a laser into the atmosphere. And if there's aerosol in the atmosphere, which there usually is, we can get back the backscatter, and that backscatter gives us, we can get velocity fields, so reds are away from the LiDAR, so that's when the LiDAR is pointing vertically here, it's just sitting on San Jose State's roof. And so as it goes away, we can calculate the vertical velocity, and then we can also measure winds coming against the beam. And so we can point it any way we want. So we have full scanning capability, we can do vertical wind profiles, and we can just measure structures through the atmosphere. For example, if we have a plume such as this is down at 400 Liggett, it's called the Stony Fire. And this plume is just kind of burning up this hill, but then all of a sudden it did this. Started rotating. And so we always try to measure, this is what we can detect these circulations ahead of time. Now if we were in Reading the day of the car fire, then we would have been able to measure these circulations. The weather radar picked it up, but so here's what that looks like with the radar, with the LiDAR. So this is a horizontal slice. The LiDAR is doing this through that plume. And so the velocities are the colored, so winds away from the LiDAR, which is here, or that way, winds towards are blue. So point this to the people who are online. Winds going away are red, winds going towards are blue, and so you can see the circulation here. And then you can also see it in the smoke, the backscatter. That's the aerosol that the LiDAR picks up. And you can actually see this clear air by the red arrow, that's cleaner air being entrained into the circulation here. And so then we can continue scanning, and so we can map this structure moving around the topography here. The dots just represent higher terrain, but you see where the reds and blues are really close together, we call that a velocity couplet. That's like a tornado-like circulation. It's not very strong in this case, but that's what we would see in something like that. And we can also go to other wildfires. This is Del Portal, and we're scanning vertically now. And so we can map out the plume structures. And so nobody had ever done this before, believe it or not. And so these are my two students here. This is Yosemite National Park off of Highway 120 before you drop into the valley. And this was a great case for us because it was burning in some tall timber, and so the plume was pretty stationary. Usually the fires are moving, the plume's evolving, so we're moving with it. But this way we just got to sit there and make about an hour and a half of scans. And if we average all those scans together, what we see here, this is the mean average of this contour here on the left is the plume boundary from the aerosol backscatter. The red line is kind of the plume mean height, or the plume center line, excuse me. And then the reds are the velocities away from the LiDAR, and the blues are the velocities towards the LiDAR. And so, look at that, you can see convergence at the base of that plume, just like what we should in our numerical modeling studies. And we didn't see it in the grass fire because the grass fire was very high wind. And it was a very small fire, so the power of the wind was greater than the power of the fire, according to our Froude number.
I have a quick question. So why is it in triangular when you're showing the simulations? There's a boundary that is triangular.
Oh, that's just the scan boundary.
Oh, the scan boundary.
Yeah, so the LiDAR goes like this, and it goes like this, stops. So we go back. The LiDAR didn't go all the way over here. It stopped right here and came back down. Went back up to here, came back down. Because we want to get as many scans as possible in the shortest amount of time, but go slow enough that we get the detail of the measurements. And so we limit our scan sector. We could scan the whole atmosphere, but it would take time, and by that time the plume did something else. So that's why it's limited. And so and so we can see this convergence at the base of the flow, or at the base of the plume. That's not that strong, it's a few meters per second, but we do measure that. On the other side, you can see that the smoke variance, so this is basically, the darker the color, the more variance. That means that there's more entrainment. The smoke is basically going from very, very thick smoke to very, very less dense smoke, right? And so the variance increases. So we get the most of the entrainment at the base of the column. And what's unique is that nobody's ever measured this before, and so a lot of smoke modelers, air quality modeling systems are using these data to validate their smoke prediction. And here's what it looks like. This is another fire, the Rag Fire of 2015, which was in the north, I think Lake County somewhere. And you can see the plume penetrate